Something new to know about similar triangles is that to show that two triangles are similar, we only need to show that one out of the two conditions is true. Meaning that for triangles, as long as one of them is true, it implies the other is true as well. And this statement only applies to triangles. For any other shape, you still need to show that both of the two conditions are met to be able to describe the two shapes as being similar. So the focus of the rest of this section will be proving this statement. And how we'll do that is, we'll look at a situation where we're told that one of these conditions is true, and then based on that information, we need to show how this would imply that the other condition has also been met simultaneously. I'll start by tackling the first rule, which is that all corresponding angles are equal. Therefore, we need to prove the statement that equiangular triangles are similar. So if we just know that two triangles have all corresponding angles being equal, then that implies that they're similar. And that can only be true if all corresponding sides are also in proportion. Let's see how this is proved. The basic situation is that we're given two triangles, ABC and DEF, and we're told that all corresponding angles are equal, meaning the angle at vertex A is equal to angle at vertex D, then angle at vertex B is equal to angle at vertex E, and angle at vertex C is equal to angle at vertex F. So given this information that the two triangles are equiangular, we need to prove that all three sides are in the same proportion. Meaning that the ratio you get when you calculate AC over DF is equal to the ratio for AB over DE and the ratio for CB over FE. So the first thing you need to do is mark a point X along this side DF so that the length of the side DX is equal to the length of the side AC. And in a similar manner, mark a point Y on the side DE so that dy is equal to AB. This would look like the following. So as required, I marked the point X on the side DF, so the length of side DX is equal to the length of side AC. And I marked the point Y on side DE, so that length of side dy is equal to the length of side AB. Therefore, dx is equal to AC and dy is equal to AB. And that's based on how I defined and constructed the points. Then, next thing to note is that angle D is the same as angle A. And we know that because that's what we've been told over here. Therefore, it's pretty clear to see that this triangle and this triangle are pretty much the exact same triangle, because we know that two sides have exactly the same length and the angle between the two sides is also equal. And this is enough information to confirm this for us. Then, since these two triangles are the same, that implies that this angle will be equal to this angle, meaning angle dxy is equal to angle C. So we've confirmed that this angle is equal to this angle. Then we also know that this angle C is equal to this angle F, because that's what we were told at the beginning over here. So since dxy is equal to C and C is equal to F, we can conclude that dxy is equal to F. And we can use the fact that these two angles are equal to make a conclusion about the line xy and FE, because if the two angles in the same corner are the same for a line intersecting with two lines, meaning if corresponding angles are equal, then that implies that the two lines are parallel. Therefore, xy and FE are parallel, since the corresponding angles are equal. And since xy and FE are parallel, we can apply some knowledge we just gained from the previous section related to proportionality of triangles. And that's by using the proportion theorem, which stated that a line drawn parallel to one side of a triangle divides the other two sides proportionally. Therefore, we can confidently say that dx over df will be equal to dy over de. And as earlier mentioned at the very start, dx is the same as ac and dy is the same as ab. So we can replace the dx in this numerator with ac and the dy in this numerator with ab. And therefore ac over df is equal to ab over de. Let's see how this applies to the diagram. She said ac over df is equal to ab over de. So we've proven that two of the sides are in proportion. And for a triangle, since there's only three sides, if two sides are in proportion and the angle included by these two sides is also equal, then that has to mean the third side is also in proportion. Therefore, based just on the information that the three corresponding angles are equal, we're able to prove that this would mean that the three sides are in proportion. Therefore, both conditions have been met, and from this we can conclude that equiangular triangles are similar. So just to write this down, ABC with the triple line notation used to indicate similarity is similar to DEF. And I may have mentioned this earlier, but just to reiterate, you should absolutely make sure that you write the letters for the different shapes in the correct order. Otherwise, this wouldn't be true. So if I had instead written this as ABC is similar to FED, that would not be true, and that would not be what we proved through this whole long proof. So even in an exam, if you are asked to prove this statement that equiangular triangles are similar, and you went through the whole process nicely, and then you mess up this last bit, you'll still lose some marks. So just be very careful with the notation and the way the letters are arranged in the name. Then the next thing is a nice and convenient new fact, which is that to prove that two triangles are equiangular, we only need to show that two out of the three angles are equal. And here's why that is true. Say for example, we have these two triangles LMN and QRS, and we know that angle L is equal to angle Q and angle M is equal to angle R. Then how do you go about determining the value of angle N? That's pretty simple. You just get it by saying 180 degrees minus angle L plus angle M. And since we know that angle L is equal to angle Q and angle M is equal to angle R, we can substitute these into this equation, giving 180 degrees minus angle Q plus angle R. And this happens to be the exact same equation we use to determine the value of angle S. Therefore, that confirms for us that angle N would be equal to angle S. And that's basically because since for both triangles, the third angle is equal to 180 degrees minus the sum of the first two angles, and for both triangles, the first two angles are equal, that means the sum would be equal for both, and therefore 180 degrees minus the sum gives the same value in both cases. Therefore, if we know that two angles are equal for two triangles, then that automatically confirms that the third angle is also equal, and we can describe the two triangles as being equiangular. Then let's apply this new information to an example question. In this example, we're given this diagram, which consists of a right-angled triangle inside of a circle, and that's the center point, and we have a few lines drawn in between. So the question doesn't give us any information directly, we just have to make sense of it based on the diagram. Then, given this diagram, here's the first question. Prove that triangle ACD is similar to triangle AOB. So we can do this using the two facts I just established, and these are that firstly, two equiangular triangles are similar. So that's the first thing, meaning the strategy is we need to show that the angles for the two triangles, meaning ACD and AOB, are equal. And then based on this, we can use a second fact just established, which is that we can prove that two triangles are equiangular by showing that two of their angles are equal. So keep this in mind that in general, in exam and test papers, when you're asked to prove that two triangles are similar, usually the simplest strategy is by showing that two of their angles are equal. The first angle we can go for is the right angle. Since we can already see a right angle in triangle ACD, so we need to see if we can find a right angle in triangle AOB. And to do so, we can draw on the third circle property that I showed in the revision section, and that is that if you have a straight line with two equal portions, in this case AB and BC, and the line at the midpoint connects to the center of the circle, that implies that the line AC is perpendicular to the line BO. So I mentioned that angle D hat is equal to 90 degrees and angle ABO is also equal to 90 degrees, since AB is equal to BC. Therefore, we know that one of the angles in both of the triangles is equal, those being ABO and D. Then we just need to show that one other angle is common among the two. Let's look at the diagram again. So we're looking at this triangle and this triangle. So there's one pretty obvious choice, and that's the angle A hat, since this angle is present in both these triangles. Therefore, A hat is equal to A hat. And since we've demonstrated that the two triangles have two angles in common, that's sufficient to confirm that triangle ACD is similar to triangle AOB. Therefore, we've proved what the question demanded. Then for part B, we need to prove that the ratio AO over AB is equal to AC over AD. To do so, we can draw on directly from what we just proved, which is that triangles ACD and AOB are similar. And we'd use this fact since all the sides mentioned in these two ratios fall along these two triangles. And since they're similar, therefore their sides are in proportion. So looking back at the triangles, we have triangle AOB is similar to triangle ACD. There's a bunch of ways you can go about proving it, but the way I'll choose is I'll compare the proportions of the hypotenuse for the two triangles, meaning AO and AC, and equate it to the longer side of the remaining two for the two triangles, meaning for triangle AOB that would be side AB, and for triangle ACD that would be side AD. Therefore, AO over AC is equal to AB over AD. Then, to get it into this form, it's just a simple case of cross multiplying and rearranging. And when you cross multiply, you get AO times AD is equal to AB times AC. Then for the first fraction, we have AO as the numerator and AB as the denominator. So just take AB to the other side and make it the denominator, and then take AD to the other side and make it the denominator for the AC fraction. Therefore proving that AO over AB is equal to AC over AD as required. So that was one possibility, and I later realized it actually would have been possible and quicker to just directly compare these two ratios. So let's go back to the diagram. So meaning we would say that the ratio of the hypotenuse over the longer side for the smaller triangle would be equal to the ratio of the hypotenuse over the longer side for the larger triangle, and that would be sufficient. But anyway, let's go on to part C. It says if AB is equal to 9 centimeters and CD is equal to 10 centimeters, determine the radius of the circle to 2 decimal places. Let's go back to the diagram. So it said that if AB is equal to 9 centimeters and CD is equal to 10 centimeters, determine the radius of the circle. So of all these labeled sides, which ones represent the radius? The two immediate ones I can see are this side AO or OA and the side OC. I'll answer the question by determining the length of AO, so using it to represent the radius. Cool, so how do we determine the length of AO? We've been told this length and this length, and we know ACD is a right angle triangle. And since this side and this side have the same length, that means the side AC would have double the length of AB, meaning 2 times 9 centimeters. And we know that CD is equal to 10 centimeters. So by simple Pythagoras theorem, we can calculate AD by saying square root of hypotenuse squared minus side CD squared. In other words, square root of 18 squared minus 10 squared, which comes to square root of 224, which can be further simplified down to 4 times root 14. Cool. So we have the length of side AD now, meaning this side. So all in all, we have the length of this side, this side, this side, and the length of this side. And we can draw upon the fact that triangles AOB and ACD are similar, so we can use their proportionality to determine the length of radius AO, since it's one of the sides of triangle AOB. And I'll directly use the ratio from part B of the question, which was AO over AB is equal to AC over AD. Then subbing in the values we already know gives AO over 9 is equal to 18 over 4 root 14. Then it's simply just a case of rearranging for AO, giving 9 times 18 over 4 root 14. And when you type that into your calculator, you get the final answer as 10,82 centimeters to 2 decimal places as required. Then let's go through one more example before looking at the second proof.